Okay, without further ado, let us look at functions. Okay, functions. There's a lot of vocabulary that goes with functions, so that we're going to try and cover all of that, and at the same time show you how they work. Functions are a particular type of equation, and they describe a relationship between two sets. There's the domain, and there is the range. The domain, these are all of your input values. And then the range, these are your output values. The other way that you can think of these, and it's often easier to think of it, these correspond with your x values, and these correspond with your y values. And the easiest way to remember that is that when we're dealing with things in mathematics, almost always, and in fact so often that you can pretty much guarantee it, you work in alphabetical order. D comes before R, X comes before Y. That's the easiest way to remember it. It's in alphabetical order. So in order to be a valid function, each item from the domain must be used exactly once. That is to say, there's only one output, there's only one range value for each domain value. Range values, however, can be used more than one time. And we can think of functions as a set of pairs. For a domain value with a small number of values, we can describe the function by giving the pairs of points. The x coordinates are the domain values, the y coordinates are the range values. Let's take a look at a brief example. Perhaps we're given the following set of domain values. 1, 2, 3, 4, and 5. A brief word about what I'm doing here. These squiggly brackets always denote a set. When you see things in squiggly brackets, it just says that this is a set of numbers. So the following is a function, and this isn't a function. This is just a set of numbers. This is a domain, but the following that I'm about to give you is the function over this domain. The function is the pair of points using these. So squiggly brackets denote a set, round brackets denote a pair of points, and we can separate the round brackets with commas. Okay, so there's the set. And we can say that this is a domain because this is a function because each domain value has been used only once in the whole thing. Okay? And because it's being used only once, we can call it a function. We can then go on to say that the range of this function can be listed out, and we just go ahead and use these range numbers. And when we're listing out numbers, when we're doing this sort of roster notation, please note, even though we've used 4 twice in our range, we only have to list it once. And then we go with the rest. Oh, I'm supposed to be consistent. We should put things in their ascending order. Although that's not strictly necessary. As long as you have all of the elements in your set, they don't necessarily need to be any particular order. Working with the same set of domain numbers, we can take a look at another one that is not going to be a function. If we're given this set, we're given this Okay, this is not a function for the simple reason that as we go through, we can see we end up using 5 as a domain range, as a domain input more than once. Because we've done it more than once, it is not a function. Another example of one that is not a function. Again, we start off the same way. It all looks like it's working just fine. We haven't duplicated anything. But then we get to the end and we discover that given that this is our domain, 1, 2, 3, 4, 5, in our function, we have 1, 2, 3, and 4. We haven't used 5. Therefore, we do not have an output for every input. Okay, so again, not a function. Continuing on. So far, sorry, are there any questions on that so far? It's mostly just vocabulary, mostly getting used to the idea that functions, for every input value, you must have one and only one output value. Just before I go on to look at other ways that we deal with functions, I'm going to give you a visual example of what that also means really quickly. So if we were to graph our functions, we have some function and it's just going along like this. There's something that's simply called the pencil test that is another way to check if something is a function. And the pencil test works like this. If you can take a pencil and draw your way vertically anywhere on your graph, and you only cross your graph once, then that's a good function. Okay? If for some reason you had a graph and it looped back on itself, so say for example somebody had graphed a circle, and you check by that same pencil test, oh, you can immediately see we end up crossing that graph twice, going straight up and down. When that happens, we can immediately say this is not a function. And that's the pencil test version of the exact same idea. For every input, there is one and only one output. Okay, moving on. Functions can also work as equations or formulas. And in doing so, we start to then develop a little bit of notation. And it looks like this. When we name functions, we usually give it a single lowercase letter. In this case, we're going with this. This is the standard generic version of our function notation. And this gets called f of x. Okay, that's simply how you say it, f of x, where f is the function part and x lets us know what our input is. So that's going to be our one variable. When we're dealing with things like f of x, it just allows us to do things a little bit more easily using the function notation. So if we were given the description, and this is the example, we're given the equation of a function that takes each domain element, adds 6, and then multiplies by 2. So our domain elements are going to be x. We know that because that's what's in the brackets. So it wants us to take each domain function. It wants us to add 6 to that and then double it. So now our function is 2 times x plus 6. The nice thing about function notation is that it then tells us what exactly we're doing in the case of actually having to put in specific numbers. So if we were told to, let's say, what happens if we let x be equal to 4? The easier way to say that is I want f of 4. As you can see, I've replaced the x with a 4 here, so that's what we do on our equation side. Whatever we've replaced x with in the brackets is what we replace x with in the equation. Okay? This 4 is that 4. So then we know that the function at 4 is going to be equal to 20. There's our input, there's our output. F doesn't have to be the letter. If we're not using F, we often use G. F we use because it's function, and G we use just because it's the next letter. So, if we're given yet another description of a function, this one is almost directly from the notes. If we're given an equation of the function g of x, we don't need that one anymore, that takes each domain element, so we get a domain element, squares it, adds 3, then takes the square root. That's what that description looks like. And that, by the way, is your process when you're being presented with problems like that. Translating from English into math is really a process of following the words and writing it down piece by piece exactly what it is they're describing to you. So start off with your domain element x, square it, put up the squared part, add 3, so plus 3, then take the square root, so I throw a square root symbol over the whole thing. Easy peasy. Now we're being asked from the examples for g of x from this function right here, what range element corresponds to a domain value of 5? In other words, what is g of 5? So again, I've replaced x with 5, so I do the same thing in my equation. I'll replace x with 5, and we'll go from there. So in this case, we end up doing this. So yes, G, to follow the questions in there, that's absolutely right. What is G? G is just another notation for our function notation, just like F. Oftentimes, and you'll see this a little bit later, when we're going through, the letter that goes in front often corresponds to whatever you're being asked for. So if you were being asked for the area of a rectangle in regards to x, it would probably be A of x. If you were being asked for the perimeter of something, it would then be P of x. A for area, P for perimeter, and so on and so forth. Often that first letter corresponds to what it is that you're being asked for. If you're not being asked for anything in particular, F and G and H are the most common letters that we use for our function notation. Another example. Given the function h of x is equal to x squared minus 3, what domain elements, if any, correspond to a range value of 21? So now we're going the other way. We're being given a range value and being asked to go back and find what that domain value is. We're asked to assume that all the domain, that the domain of h is all real numbers, so there's no restrictions on our domain. Because of that, we can then go ahead and say, if we're being asked what the output is going to be, or what the input is going to be if our output is 21, then we can rewrite this pair of equations so that they're equal to each other. And from there, we can just go ahead and solve. X squared minus 3 is equal to 21. I will add 3 to both sides. When I do that, I get x squared is equal to 24. I'm just looking for x, though. So x, in this case, is going to be equal to plus or minus the square root of 24, which is to say x will be equal to 2 root 6 or negative 2 root 6. A brief word on this. I'm not sure that we've looked at why radicals sometimes come out as plus or minus. So I'm just going to show why that is over here for a quick moment. If you're being asked for, example, the square root of 9, well, there's two ways that we can get to 9. We can get to 9 using positive 3, or we could get to 9 using negative 3. So the square root of 9 is technically plus or minus 3, because negative 3 squared gets me to 9, and positive 3 squared also gets me to 9. Which is why we're then being asked to do a plus and a minus version. In relation to that, we then start to look at what are the possible restrictions on the domain. So our answer here is going to depend on what our domain actually is, what we're allowed to use for our x values. For example, if our domain was all positive real numbers, so if it was just the positive real numbers that we were looking for, then we would just want that answer. Okay. If it was just asking for integers, which is to say whole numbers positive and negative, from negative infinity to positive infinity, then there would be no answers because neither of these is actually an integer. So it very much depends on what your restrictions are on your domain, if you're given any. How are we doing so far? Everybody still with me? Okay, everybody's largely with me here. Great, thank you. Carrying on then. Many of the formulas we saw in geometry way back at the beginning can be thought of as functions. And now what I'm going to talk about in here is I'm going to talk about functions in relationship to a specific variable. So if I start to confuse you, please make sure that you ask questions through this because there are a number of places where this gets asked. So if we consider a right angle triangle, I'll just draw a quick picture of this for everybody's reference. There's our right angle. And say we're given a side 4. We don't know the height. The height is variable, so we'll use it as an h, and our hypotenuse will just simply represent with a c. Let's consider the formula for the area of a triangle. In this particular case, we'll take the area in relationship to its height. So we'll take a of h, because h is the formula, or is the variable that we want this in relationship to. Our formula for the area of a triangle is 1/2 base times height. So I can take 1/2, our base is 4. Our height is a variable, so it's h, no problem. And then I'll clean that up. I can take 1/2 of 4. So it ends up being 2h. So our function for the area of a triangle in reference to h is going to be 2h in this case. We can also find the length of the hypotenuse in this triangle. Okay, so in this case we're going to go with c of h because I want to find the hypotenuse of this triangle with regards to h. We know the formula for the hypotenuse of a triangle, which is going to be that c squared is equal to h squared plus 4 squared, right? A squared plus b squared equals c squared, so h squared plus 4 squared equals c squared. I don't want c squared though, I just want c. I can square my 4 at the same time, so c is going to be equal to the square root of h squared plus 16. Now I've got my hypotenuse in relationship to one variable h, so I can say that c of h is equal to the square root of h squared plus 16. This is going to be one of those places where, although you could end up with two answers here, we're only going to want the positive answer, simply because you can only have a positive area on your triangle or positive lengths on your triangle. We can't have any negative lengths. Now with this, we can carry on and do some interesting things. So we might be asked, for example, to find the function h of c. So I'm just going to pull this out. We're going to find h of c, which gives the height of the triangle in terms of the length of the hypotenuse. Okay, so we want to find the height of the triangle with regards to the length of the hypotenuse. Well, we already had a relationship between c and h here. We can go ahead and use that same relationship. So we know that c squared is equal to h squared plus 16. I'm going to get h on its own, so I'm going to subtract 16 from both sides. And when I do that, I will get c squared minus 16 is equal to h squared. I just want h, so I'm going to take the square root on both sides, and h will be equal to the square root of c squared minus 16. So now the height with regard to the hypotenuse will be c squared, square root of c squared minus 16. Carrying on with that same idea, we can go right back to our original formula, okay, where we originally found the area with regards to the height. I'm now going to find the area with regards to the hypotenuse. Here I found that any place that I had h, like there, I could replace it with the square root of c squared minus 16. So that's exactly what I'm going to do. So a of c now becomes equal to 2 times the square root of c squared minus 16. Did everybody follow that? Fantastic. Oh, just a momentary update. Things have changed radically while I've been talking with you. Okay, looking at some applications of all of this. Let's look at profit, cost, and revenue functions. Here's an example. A restaurant has X number of customers per day. X number of customers per day. Each customer buys a lunch special, which has a price of $10. No problem. The restaurant has fixed costs of $1,400 for rent and electricity, etc., and each lunch special costs $4 to prepare. So there we go. Our lunch costs $10 for the customers. It costs us $1,400 to run the place, plus $4 per lunch. So now we want to find some equations. We want to find R of X, which is going to represent the revenue. We want to find C of X, which is going to represent our costs. Let's see if I can write that so it's clearly. Revenue. These are our costs. And then P of X, which will represent our profit. Okay. So revenue. Lunch costs $10. We have X number of customers per day. So R of X is simply going to be 10X, $10 for every customer that buys a lunch. Our costs, well, our costs, we have a fixed amount of $1,400, and it's $4 for every lunch, so 4X. Every time somebody buys a lunch, it costs us $4. So then our profit is always going to be our revenue minus our costs. And there we can see a simple way that we can use the function notation to put together multiple expressions. Profit is going to be revenue minus cost. So now I can actually replace R of X and C of X with what R of X and C of X are actually equal to. So R of X is 10X, so I go ahead and put it in place. C of X is 1,400 plus 4X. And please take note, I've put C of X in brackets because I'm trying to subtract the whole thing. And when I go to take away the brackets, that negative distributes now. So this becomes 10X minus 1,400 minus 4X, and then I put together my like terms, and I end up with 6X minus 1,400, and there's my equation for the profit. Now that we've got an equation for the profit, we can go ahead and do some calculations. So if we were asked what is the profit made from selling 1,000 lunch specials, we can actually come along and ask ourselves, well, what is P of 1,000? Not 100, 1,000. And when I do that, I can go ahead and say I want 6 times 1,000 minus 1,400, which is to say I want 6,000 minus 1,400 for a simple 4,600. Any questions on that? Okay. Determining the domain of a function, which is to say, how can you determine where x lives and what the possible restrictions on x might be? To find the domain of a function, it's often easier to think of which values of the domain would cause a problem. Okay? Things that cause problems. Anything that makes the domain 0. Or sorry, that makes your denominator 0. Which we'll talk about in just a second. Another place where we have problems is any value that causes the inside of a root and I will be specific, an even root to be negative. And we'll take a look at two possibilities there. So, for example, if I had something, let's go with an example, sorry. If I was given the equation f of x is equal to 1 over x minus 4, what would be the danger here? The danger is when the denominator is equal to 0. So what I'm looking for is where does x minus 4 equal 0? Well, x minus 4 equals 0 when x is equal to 4. So for here, what I would want to say is that my domain is going to be any place where x does not equal 4. Because that's what sends it to 0, so that's a problem. Similarly, using the same idea, if I was given f of x is equal to the square root of x minus 4, well then, anything that's going to turn this negative is going to be anything where x is less than 4. Right? Because if x is less than 4, then we're into negative numbers. So for this, my domain simply has to be any x that is greater than or equal to 4. Any questions on that? Not yet. Let me do a couple of examples. Okay. So we're given a function. One over x squared minus 25. And we're asked to define where this function, where the domain of this function is. So what we immediately look for is the place where our denominator goes to 0, which means I'm looking for any place where my x squared is equal to 25, which means I'm looking for any place where x is equal to plus or minus 5. Which means for my domain, I'm looking for x to not be equal to, the square root of 25. Let's get that right, so plus or minus 5. So I'm looking for any place where x is not equal to 5 and where x is not equal to negative 5. Going on to my next example, again looking under the square root problem. So now let's say that we're being given the function g of x, and it's equal to the square root of 2x minus 5. We're looking for any place that keeps this positive, so we need 2x minus 5 to be greater than or equal to 0. Which means that 2x needs to be greater than or equal to 5, which means that x needs to be greater than or equal to 5 over 2. So then we can say that our domain will simply be x greater than or equal to 5 over 2. Okay, and then just looking at the last couple of examples. We can do operations with these functions. We can carry out something. So if we're given the following pieces of information, we're being told that we have a function f of x, which is equal to x squared plus 5x plus 6, and we're being given g of x, which is equal to x squared minus 4. And then we're being asked to simplify the following. Make sure I get this the right way. What we're being asked to simplify is g of x divided by f of x. So, step 1 with g of x divided by f of x, replace g of x and f of x with their actual equations. So, g of x is equal to x squared minus 4, f of x is equal to x squared plus 5x plus 6. Setting it up is half the battle. Once we've set that up, then we carry on with what we know we're supposed to do. We start factoring. X squared minus 4 is a difference of squares, so I get x minus 2x plus 2. Here I'm looking for what multiplies to 6, but adds to 5. The answer there is 2 and 3, so this becomes x plus 3, x plus 2. I recognize that x plus 2 and x plus 2 can cancel out. And we're left with a very simple x minus 2, x plus 3. And that's our final answer. One more example really quick before I wipe this out. If we're then given another request, we're being asked to do f of x minus g of x. Same process applies. Make sure that you're writing these things down. And out of habit, write them down in brackets so that when you have minuses, you know that you have to apply them. Okay, so there's a minus and it's going to distribute in here. So when I start to simplify this, I end up with x squared plus 5x plus 6 with no changes, no problem, minus x squared plus 4. My x squareds cancel out because I have one positive and one negative. I can put 6 and 4 together. So I end up with 5x plus 10. So the other thing that we can do with function notation, now that we have all of these things, is we can replace x with just about anything we want, including other functions or expressions. So let's say that we're given this same f of x function, x squared plus 5x plus 6. If we were asked to evaluate f of 3, that would simply be replacing our x values with 3. So that becomes 3 squared plus 5 times 3, which gets us 9, plus 15, plus 6, which gets us to 30. No problem. If we were then asked to replace or to evaluate f of x for a minus 1, the same rules apply. Whereas we replaced x with 3 in this equation, now I'm going to replace my x's with a minus 1. So I end up with a minus 1 squared plus 5 times a minus 1 plus 6. A minus 1 squared becomes a squared minus 2a plus 1. 5 times a minus 1 becomes 5a minus 5. And then the 6 comes along. We put together what can put together. There are no other a squareds, so it comes down. I have negative 2a, positive 5a, so that ends up as a 3a. Negative 5 and positive 6 is 1 plus another 1, and we end up at 2. Okay. Any questions on any or all of that? So I quickly update the score. Okay, fantastic. We've had a quick 40, 50 minutes worth of